Electoral ESPOL les da la bienvenida al conversatorio Jornada Científica STEAM, Cómo aportar al mundo a través de la ciencia. Este conversatorio se realiza bajo el marco de la visita a nuestra ciudad de 4 premios Nobel que hoy nos acompañan en la ESPOL para compartir sus conocimientos y experiencias para futuros científicos y que estos puedan aportar al mundo a través de la ciencia. Antes de iniciar este programa, quisiéramos agradecer a la empresa municipal de turismo y a la Fundación Fidal, quienes han hecho posible la visita del día de hoy. También agradecemos la presencia de autoridades nacionales, locales, representantes de gremios, estudiantes y directivos de varios colegios de la ciudad y, por supuesto, a nuestra querida comunidad politécnica. A continuación, invitamos a la doctora Cecilia Paredes, rectora de nuestra institución, quien nos brindará las palabras de bienvenida.
Buenos días, ¿cómo están? Eso, muy bien, me alegro mucho. Estimada doctora Rosalía Arteaga, expresidenta de la República del Ecuador y presidenta de la Fundación para la Integración y el Desarrollo de América Latina, FIDAL. Señora Gloria Gallardo, presidenta de la Empresa Pública Municipal de Turismo. Dr. Aaron Ciechanover, Premio Nobel de Química 2004. Sir Richard Roberts, Premio Nobel de Medicina 1993. Dr. Richard Schröck, Premio Nobel de Química 2005. Dr. Erwin Neher, Premio Nobel de Medicina 1991. Jean Roberts, profesora y coach. Nancy Schröck, maestra con experiencia en problemas de aprendizaje. Dr. Eva Maria Neher, científica alemana y directora ejecutiva del Göttingen X-Lab. Estimado vicerrector, estimadas autoridades elegidas del ESPOL, decano Monsalve, decana Romero, estimados profesores, estimados rectores, estimados estudiantes, público en general. Bienvenidos al ESPOL. Welcome to ESPOL. On behalf of our university, I give you the warmest welcome to our campus, which has proudly received before inspiring experiences of important personalities in science and technology. But today is historic for us. This is the first time we have 4 Nobel laureates here in ESPOL and in Guayaquil. Thank you for your generosity, for coming to our country, to our city. It is extremely important to us to encourage these children and children from all over Ecuador to fall in love with science and follow its path. After COVID pandemic, more people around the world realize that science is indeed the difference between life and death. Certainly to solve problems, even problems we are not aware yet. We need more children, little kids, to fall in love with science and to begin its path. We show great respect to Nobel Prize winners. It is without a doubt a long, very long route, beginning with vocation, curiosity, questions, and concerns. They have to develop several skills to pursue funding, experimentation, network creation, team building, group effort. For ESPOL, this is an important moment as an Ecuadorian top public university, since we strongly believe that research, science, and innovation is the way to develop our country. Queridos invitados, ¿qué mejor escenario para nuestros estudiantes, científicos, académicos e invitados puedan conocer de primera mano a representantes de la élite mundial en ciencias y saber de sus aportes e investigaciones relevantes para cambiar nuestro mundo, para cambiar nuestras vidas? Conocer sobre su legado a la humanidad. Muy pocos saben el camino para llegar a ser un premio Nobel. Es un camino arduo, largo, de cuestionamientos, de vocación, de perseverancia, de trabajo en equipo, de cuestionarse una y otra vez, de buscar la respuesta a todas esas preguntas que significan, como mencioné, la diferencia entre la vida y la muerte, entre la solución del problema, entre mejorar nuestras vidas. En ESPOL creamos soluciones a partir de la ciencia, porque creemos en ella. La agenda que hemos preparado está basada precisamente en conectar las especialidades de nuestros ilustres visitantes con nuestros expertos politécnicos, con el gran objetivo de lograr ese intercambio de experiencias, esa retroalimentación que nos beneficiará e inspirará a seguir creando valor a nuestra sociedad. Y es que hoy tenemos la oportunidad de escuchar y preguntar y de intercambiar ideas con Ciechanover, Premio Nobel de Química 2004, de conocer más sobre el trabajo de Sir Richard Roberts, Premio Nobel de Medicina 1993, y Jean Roberts, profesora, psicóloga y coach, de aprender de Richard Schröck, Premio Nobel de Química, y de su esposa Nancy, maestra de escuela con vasta experiencia en educación infantil y problemas de aprendizaje. Así también como escuchar con atención a Erwin Neher, Premio Nobel de Medicina 1991, y su compañera, la doctora Eva María Neher, científica alemana en los campos de bioquímica y microbiología y directora ejecutiva del Göttingen X-Lab. Bienvenidos a este evento que se realiza gracias a la Empresa Pública Municipal de Turismo, Promoción Cívica y Relaciones Internacionales de Guayaquil, a través del Buró de Convenciones y Visitantes, la Fundación para la Integración y el Desarrollo de América Latina, FIDAL. Gracias por confiar en nosotros, gracias por confiar en ESPOL, en quien siempre tendrán una aliada y su casa. Ahora arrancamos con el conversatorio Cómo aportar al mundo a través de la ciencia. Y en la tarde, Richard, Aaron, Erwin y Sir Richard participarán en coloquios especializados y recorrerán nuestros centros de investigación del ESPOL. Mientras eso sucede, nuestras científicas del área STEAM, ciencia, tecnología, ingeniería, arte y matemáticas, podrán reunirse con Jean, Nancy y Eva María para el conversatorio Mujeres y la Ciencia, cómo crecer personal y profesionalmente siendo una mujer en ciencia. Además de escuchar su experiencia y recorrer nuestro parque de ciencias AJA. Una jornada que estará llena de conocimientos y ciencia. Gracias a todos por ser parte de este evento, histórico para nosotros. Y gracias a todos por creer en la ciencia. Muy bienvenidos a la ESPOL.
Gracias por sus palabras a nuestra querida rectora, la doctora Cecilia Paredes. Y en este momento vamos a recibir a la señora Gloria Gallardo, directora de la Empresa Municipal de Turismo. Recordamos que la Empresa Municipal de Turismo y la Fundación FIDAL hicieron posible este encuentro hoy con 4 premios Nobel en nuestra universidad. Bienvenida, Gloria, buen día.
Buenos días a todos. Doctora Cecilia Paredes, rectora del ESPOL, doctora Rosalía Artiaga, presidenta de la Fundación para la Integración y Desarrollo de América Latina, FIDAL, doctor Ciechanover, Premio Nobel de Química 2004, Sir Richard Roberts, Premio Nobel de Medicina 1993, doctor Richard Schröck, Premio Nobel de Química 2005, doctor Erwin Neher, Premio Nobel de Medicina 1991, doctora Eva María Neher, científica alemana y directora ejecutiva de Göttingen X-Lab, doctor Paul Herrera, vicerrector académico, doctor Carlos Monsalve, decano de investigación, doctora Paula Romero, decana de la Facultad de Ingeniería en Ciencias de la Tierra, autoridades del municipio de Guayaquil, colegas, estudiantes e invitados especiales. Estar aquí en la ESPOL es un honor y frente indudablemente a un auditorio de jóvenes estudiantes que definitivamente son el presente y el futuro de esta ciudad y de este país. Y que estén aquí ustedes frente a ellos, a los premios Nobel que nos visitan, que como bien dijo Cecilia, ganar un premio Nobel es un largo proceso y ser parte de querer saber mucho más, ligarnos con la ciencia y preguntarnos y cuestionarnos. Y ellos están aquí y ustedes tienen un privilegio enorme, poder escucharlos, poder interactuar. Y lo que esperamos con este evento es que se motiven por la ciencia, porque aquí tenemos una científica que tiene un programa, la científica Neher, que tiene un programa precisamente para que los estudiantes se motiven por la ciencia y que hagan de la ciencia una carrera. Ustedes saben mejor que nadie que ellos, al igual que todos los premios Nobel y todos los investigadores que hay en el mundo, ¿qué es lo que hacen? Dar todos sus conocimientos en bien de la humanidad, en bien de todas las actividades que se necesitan, especialmente en la salud, en el desarrollo tecnológico, industrial, comercial, etcétera, en la educación. Y todos ustedes conocen que si no se eleva la educación de una sociedad, nunca en los países subdesarrollados o en desarrollo podremos salir de la pobreza. La educación es todo y realmente por eso nos esmeramos nosotros como municipio de Guayaquil, la alcaldesa, doctora Cintia Vitere, que trabaja muchísimo por los jóvenes, por los niños y sobre todo en la educación y en la salud, de que tengan las oportunidades que merecen. Y esta es la forma también de apoyar a la educación. Traer eventos de esta naturaleza, ¿para qué? Para beneficio de ustedes, de la sociedad, porque aquí Cecilia nombró lo que es el Buró de Convenciones de Guayaquil. El Buró de Convenciones de Guayaquil es una entidad que está bajo mi responsabilidad con un gran equipo para atraer a la ciudad congresos, ferias, convenciones de alto nivel científico, cultural, educativos, deportivos, etcétera, etcétera. Y hemos tenido tal resultado a base de ¿qué? De amar lo que se hace, de hacer con pasión lo que se ama. Y se trae como consecuencia que Guayaquil se haya convertido en el destino más importante del país de reuniones y que hayamos hecho solamente del 18 al 20 más de 369 congresos con una derrama económica de 626 millones de dólares. Y tenemos este año, la pandemia nos golpeó, perdimos 615 millones de dólares, pero ¿qué sucedió? Nos volvimos a levantar porque esta ciudad se levantó de la pandemia en un ejemplo admirable, no solamente ante el país, sino internacionalmente. Y nosotros fuimos la primera ciudad en el mundo con un aforo del 30% para continuar con los congresos y convenciones. Y no detuvimos nuestra marcha. Y por eso me dirijo a ustedes para decirles que más allá de la importancia de la derrama económica, que definitivamente refleja la generación, el valor de la cadena del turismo, que genera empleo y bienestar para todos, está el intercambio de conocimientos. Y eso es lo que hace este tipo de eventos, intercambiar los conocimientos. ¿Para qué? Para nutrirse ustedes de ellos, que se cuestionen también, que aprendan, porque la vida es un aprendizaje eterno hasta que nos muramos. Y de allí sabe Dios qué puede suceder. Pero lo cierto es que aprovechemos esta gran oportunidad, escúchenlos, motívense, den gracias a Dios por tenerlos aquí y les doy la bienvenida también a nombre de la alcaldesa, a nombre mío, y que esta jornada sea un éxito definitivamente para todos. Guayaquil los recibe con los brazos abiertos y estoy segura que se llevarán en su corazón nuestra ciudad y su gente. Muchísimas gracias.
Agradecemos las palabras de la señora Gloria Gallardo. Y eventos de este nivel efectivamente logran que Guayaquil se siga destacando como un destino turístico. Gracias a todos por acompañarnos esta mañana. Para esta visita también hemos contado con el apoyo de la Fundación Fidal, representada por la doctora Rosalía Arteaga, quien nos dirigirá unas breves palabras.
It is a pleasure to be here and to welcome you, all our distinguished guests, to this very special event here in ESPOL. I'm going to switch to Spanish because you have the translation. Gracias a todos por estar aquí. Un saludo muy especial a la rectora Cecilia Paredes, a Gloria Gallardo, presidenta de la empresa municipal de turismo, a las distinguidas autoridades, hombres y mujeres que en la ESPOL están trabajando por una educación de calidad. Saludar al doctor José Ramón Calvo, director del Instituto de Asuntos Internacionales de la Real Academia Europea de Doctores, a Claudia Arteaga, a Cecilia Kindelan, a las distinguidas personas que acompañan esta delegación y que mañana harán su traslado a las Galápagos para una gira de observación a bordo del Endeavour, este barco de National Geographic que hace el recorrido en nuestras islas, y pretendemos de allí sacar un manifiesto también a favor de la preservación de las Galápagos. Quiero saludar a una chica especial que está aquí. Ella vino cuando supo que había este evento. Es una niña que sueña con ser astronauta y ella, al igual que 9 chicas ecuatorianas, el día 4 de septiembre van a viajar a la NASA. Han tenido una preparación de algunos meses y hemos conseguido varias organizaciones, She's Astronaut, Fidal y otras instituciones, trabajar para que ellas cumplan su sueño y vayan a la NASA. Son niñas jovencitas de 12, 13, 14 años que cumplirán ese sueño. Fidal viene trabajando con mucho entusiasmo desde hace algunos años en propiciar la inclusión de chicos y chicas en las metodologías STEM. Tenemos un acuerdo con la Academia de Ciencias de Nueva York y venimos desarrollando un currículum para escuelas que evidentemente está dando ya su fruto, tanto por capacitar a niños y niñas como también a profesores para que estimulen la creatividad. En nuestro país, desafortunadamente, la creatividad tanto artística como científica a veces se mata en las escuelas. Y creemos que es fundamental el desarrollar todas esas actitudes y aptitudes para que nuestro país tenga una calidad de vida mejor, para que aportemos a la ciencia. Yo no quiero abusar del tiempo aquí en este micrófono porque hemos venido a escuchar a los Nobel, pero quiero hacer la invitación a todos ustedes porque con Fidal tendremos los días 28 y 29 de septiembre en el Palacio de Cristal un gran evento, una gran feria de educación. Y el día 29 a las 5:30 de la tarde en el mismo Palacio de Cristal estaremos premiando a los mejores profesores de Ecuador y de Iberoamérica. Alguna vez un profesor del COPOL ganó una distinción de esta naturaleza y aspiramos a que muchos más profesores y profesoras puedan estar inmersos en el mundo fantástico de la ciencia y de impulsar a nuestros niños y jóvenes para salir adelante. Queremos desear que esta sea una jornada, el día completo, dedicado a la ciencia y a escuchar a mentes brillantes que están aquí con nosotros. Muchas gracias.
Gracias también a la doctora Rosalía Arteaga por sus inspiradoras palabras. Vamos ahora a proceder con el conversatorio que nos convoca esta mañana y para el cual invito a acercarse al moderador de este panel tan prestigioso que presenciaremos. El doctor José Ramón Calvo, presidente del Instituto de Cooperación Internacional de la Real Academia Europea de Doctores. Él es asesor estratégico del Barcelona Supercomputing Center, doctor en Medicina, catedrático de Educación para la Salud en la Universidad de Las Palmas de Gran Canaria, fundador y director del Campus de Excelencia. Además, director ejecutivo de la Oficina Española del International Center for Migration, Health and Development, asesor de Climate Change Reality Project liderado por Al Gore. El doctor Calvo también es autor de numerosos libros, artículos y reconocido conferencista internacional. Bienvenido, doctor Calvo. Le cedo la palabra.
Muchas gracias. Muchas gracias. En primer lugar, debo decirles que para mí es un extraordinario honor que agradezco básicamente a la rectora, a la Fundación Fidal y por supuesto al órgano municipal de turismo de Guayaquil, en la persona de su presidenta, doña Gloria Gallardo, el haberme dado el honor de compartir con mis 4 amigos la satisfacción de poder hablar sobre ciencia, que es lo que más les gusta. Pero teniendo en cuenta que en esta audiencia, y yo voy a ser muy breve porque creo que a quien hay que escucharles es a ellos, no a mí, pero en esta audiencia hay un grupo de jóvenes interesados y preocupados por mejorar su futuro. Tal vez sea bueno empezar diciéndoles por qué es importante haber recibido el Premio Nobel. Porque a veces, sobre todo lo hemos visto a veces con periodistas, preguntan cosas un poco absurdas, ¿y usted qué hizo en la vida? No, el Premio Nobel es probablemente, y casi sin probablemente, el mayor honor que un científico puede recibir. ¿Por qué? Porque está reconocido mundialmente por sus pares como alguien que ha hecho algo muy relevante, muy interesante, muy único, que ha salvado muchas vidas, que ha conseguido hacer algo que el resto no habían hecho. El Premio Nobel nace a partir de la voluntad de un empresario sueco, Alfred Nobel, quien decide crear estos premios a su muerte. En un testamento, él decide donar su fortuna para que se pudieran premiar a los mejores descubrimientos que se dieran en el mundo de la medicina y la fisiología, en el mundo de la física, en el mundo de la química, en la mejor obra literaria y en la paz, en la persona que hubiese conseguido el mayor desarrollo o desempeño para conseguir la paz en el mundo. Posteriormente, muchos años después, ya en la final de la década de los 70, se crea el Premio Nobel de Economía, que no es realmente un premio Nobel en el sentido que no fue creado por Alfred Nobel, pero fue un premio creado por el Banco de Suecia en honor y homenaje a Alfred Nobel, y por tanto lo entrega la misma Fundación Nobel y a los efectos prácticos se le considera el último premio Nobel. Así que hecha esta pequeña disquisición sobre el premio Nobel y para que sepan cuál es un poco la historia del mismo, me gustaría presentarles a nuestros invitados. Y la presentación va a ser muy breve porque, repito, yo creo que a quien hay que oírles es a ellos. Y fundamentalmente, si ustedes consultan en cualquier, digamos, de las informaciones que hay en la red, podrán ver quiénes son. Pero yo les haré un brevísimo apunte biográfico de cada uno de ellos para que ustedes al menos sepan quiénes son las personas que les van a dirigir la palabra. Y el primero de las personas a las que me voy a dirigir es el doctor Erwin Neher. Erwin Neher es físico, él estudió física en la Universidad Técnica de Múnich y en Estados Unidos se especializó en fisiología. Trabajó como investigador en las universidades de Wisconsin y Yale y en el año 1983 fue nombrado director del Departamento de Membranas del Instituto Max Planck de Göttingen. El doctor Neher investiga los principios biofísicos y moleculares del flujo de información entre neuronas y junto con su amigo, el doctor Bert Sakmann, desarrollaron una serie de técnicas que permiten medir el flujo de iones entre los canales de las membranas celulares y por eso recibió el Premio Nobel. El doctor Richard Royce Schröck, que tengo aquí a mi izquierda, es químico y es profesor universitario del muy prestigioso Massachusetts Institute of Technology, el MIT. Él recibió el Premio Nobel de Química en el año 2005, cursó la carrera de Química en la Universidad de California y en Harvard, donde se doctoró, y luego hizo estudios postdoctorales en la Universidad de Cambridge. Trabajó para la muy famosa compañía química DuPont, y luego, años después, entró a trabajar en el MIT, donde desde 1980 trabaja y sigue siendo un docente. Realmente él hizo algo que para los que no somos químicos se convierte en algo difícil de explicar y mejor que lo explique él que no que les diga yo, qué es lo que es, porque probablemente lo liaría. Porque si yo les digo a ustedes que su trabajo trata del campo de la metatesis olefínica, especialmente a través de los alquenos, es probable que para ustedes les suene igual de chino que para mí. Entonces prefiero que sea él el que lo explique. El caso de Sir Richard John Roberts, él nació en Inglaterra, pero estudió inicialmente química, aunque después ya posteriormente desarrolla una actividad docente como investigador, y actualmente ya hace muchos años que trabaja en una pequeña empresa dedicada a la biotecnología, pero que pequeña en tamaño, pero grande en capacidad y en producción. Ya después hablaremos de las últimas cosas que han hecho en el tema de COVID. Fueron capaces de desarrollar test rapidísimos para determinar y poder diagnosticar COVID, y también participar en toda la elaboración de vacunas. Él obtuvo el Premio Nobel de Fisiología y Medicina en el año 1993, compartido con Philip Sharp, por su trabajo sobre unos fragmentos de ADN que de alguna manera describen la información depositada en un gen, y que yo también le dejaré que sea él el que lo describa después. Nuestro tercer invitado, el doctor Ciechanover, es biólogo y médico. De hecho, él es cirujano, aunque su premio Nobel fue en química. Y realmente Aaron ha estado trabajando durante gran parte de su vida en el Instituto Tecnológico de Israel, el Technion, es uno de los grandes centros de investigación del mundo sin ninguna duda, y él dirige allí el Instituto Rappaport de Investigación en Medicina. Aaron estudió junto con su colega y en aquel momento mentor Abraham Hershko la degradación de las proteínas, y descubre que esa degradación está regulada por un mecanismo que se llama las ubiquitinas. También él les explicará mejor que yo de qué trata esa historia, que es fundamental además para la creación de nuevos fármacos. Y por último, tengo a mi lado, ya los tengo todos, ya los presenté a todos, pues ya no hay más que hacer. Now I will start, with my first question that will be common for all of you. That, as you can see, we have a lot of students from different ages and different levels. I would like to try that you can explain each one of them the reason because you become a scientist, and the reason because you received the Nobel Prize after your research in different fields that you was working with. And then I will start with Erwin Neher, that is on my right side.
Well, you for invitation to be here. It's a pleasure to be here. Regarding your question, why did I choose my research field and how did it lead to the Nobel Prize? Let me make it very short. I was already interested as a high school student in the fact that there is electricity in our body. You know, I was reading about. Yeah, can you hear me now better? Okay, thank you. Let me repeat. Already as a high school student, I was interested in the fact that there is electricity in our body, and I wanted to know more about it. So I decided to become a biophysicist because I was also interested in electrical appliances and everything technical around me. So I had to make a decision. Do I want to study biology or physics? Because the combination, the interdisciplinary kind of programs didn't exist at the time when I was a student. So I decided to start with physics and to switch on to biology as soon as I could. So already as for my PhD project, I was looking for a topic which would satisfy my interests, and I was lucky to find a laboratory in Munich by Dieter Lux, which gave me a thesis project for the study of ionic currents in snail neurons, in the neurons of the snail, of the garden snail. This was very interesting. I learned everything about electrophysiology, and at that time, the dominating theory about how a nerve action potential works was done by British physiologists, Hodgkin and Huxley, who had shown that when a nerve action potential, a nerve signal originates, this comes about by the fact that the membrane which is surrounding the neuron becomes permeable to ions. It becomes permeable first to sodium ions, which flow inside, makes the inside positive, and then afterwards it becomes permeable for potassium. Potassium flows outward and reverses the signal. So the real pressing question at that time was, why does the membrane become permeable? Why do suddenly pathways for ion flux open? And Hodgkin and Huxley had already formulated their experiments in terms of ion gates which were supposed to open and close. Many people were against this interpretation because there were arguments, why should it be so specific for certain ions, simple gates cannot do it. So Bert Sackmann, who was a fellow student in Munich at the time, and myself came together and discussed this problem, why can this happen? And a few years later, when we met again as postdoctoral fellows in Göttingen, we decided to try to prove the Hodgkin-Huxley concept of channels open and closing by trying to measure the currents as sensitive as possible, with the idea of possibly we could demonstrate that there's actually stepwise changes in current when such single channels open and close. And of course, we had a problem. The signals we were supposed to measure, which we wanted to see, were of an order of magnitude about 100-fold smaller than anything which could be measured at that time in terms of currents in biological tissue. So we had to come up with an improvement of methods by a factor of 100. And for this, we followed a very simple idea. We argued that if you want to measure a very small current, it's not wise to measure the current from a whole cell, which was standard technology, but to try to measure currents from a small patch of membrane. And so what we did is we placed a measuring pipette onto the surface of a cell instead of trying to punch into the cell, which was standard practice. And well, the idea worked. It's very simple. I mean, you just measure the current from a small patch of membrane with a small glass pipette. Of course, we had to solve a few technical problems, but we were lucky. It worked. And after a few years, after 4 years of work or so, we actually could demonstrate very convincingly that there are these stepwise currents which do show the observed statistical behavior, that the switching events are not deterministic but stochastic, and so on. And this just proved the concept, and it opened a way to study basically all electrophysiology 100-fold more sensitive than before. And this turned out to have very big relevance for pharmacology. Also it turned out that dysfunctional channels are the reason for many hereditary diseases and so on. So it just became a very important issue in biomedicine, and that in the end led to the Nobel Prize.
I don't know. Yes. Thank you very much, Erwin, for... I would like now to ask Ciechanover more or less the same question. He's a passionate of the science, of the dissemination of the knowledge, and in fact, I know Aaron a long time ago, and from the beginning, I realized that he's a real passionate of science and is passionate of the work that he's doing. And I would like to, you can share with the audience all this thought that you have about science and the reason that you was involved in science, because you was a medical doctor and surgeon, and then start to talk to work in the lab, and then discover the ubiquitin system. And okay, explain the audience about everything that you thought about that.
Can you hear me? So, as you mentioned, Jose Ramon, I was educated as a physician and as a surgeon, but I realized that in medicine, when the patients are getting to the hospital, in many cases, it's much too late. So the disease has evolved along many years. Let's take neurodegenerative diseases like Parkinson or Alzheimer or heart diseases. The cholesterol has been accumulated for decades, and what the physicians is seeing is basically the end result. And I was kind of thinking naively about what are the roots of the disease, why people are getting sick from the beginning. It was very naive at the time, and it took 30 years for me to travel through science in order to understand that it was not that naive after all. And I decided to go to science because I realized that the answer to this question about the root of diseases is buried in science. And I joined Avram Hershko, who just was a young scientist at the time, just came back from his own postdoctoral fellowship. So I stopped my training in surgery and moved to the lab. And since I'm coming from a very small country, much smaller than Ecuador, we are barely 9 million people, we decided to take kind of a surprising way. The whole world was busy at that time with the central dogma of biology, with the genetic code, how DNA is transcribed into RNA and how RNA is translated into DNA. And we decided to go to the opposite side, how proteins are destroyed. So nobody is interested in destruction. Everybody is interested in construction. Destruction is not something that attracts people, but we realized that protein degradation has many roles, and I'll come to it in a minute. And we embarked on this question, and we discovered the ubiquitin system. I will allude into it later on in a more specific lecture. Took us several years to unravel a novel mechanism by which the body is removing damaged proteins. Proteins are very sensitive to damage. They are sensitive to oxidation. They are sensitive to temperature. Don't forget, we are living in a very high temperature that proteins do not tolerate. It's not the temperature in Ecuador during the hot season. It's the temperature of the body. 37 degrees is a very high temperature. We don't feel it as hot, but nevertheless, for proteins, it's a problem. And as you know, in your homes, you are keeping your proteins in the refrigerator. You are putting, or in the freezer, you are putting the meat, the cheese, the milk, the eggs. These are all proteins. The fish in Ecuador, the shrimps, you are putting in the refrigerator. The high temperature of the body is not a good temperature for proteins, and they are, even in the body, they are getting damaged all the time. Proteins get mutated because of genetic reasons, because of irradiation, and so on. And there must be a mechanism to remove damaged proteins. And damaged proteins, if they are not removed properly and on time, are causing damage, are causing diseases. Among them are cancer, oncogenes are mutated proteins. Among them are all the neurodegenerative diseases like Alzheimer and Parkinson that are being caused by aggregated proteins in the brain. So there is a huge importance for a system which is a quality system that will detect and identify these damaged proteins and remove them. And we discovered this system, which after the discovery, it became a huge industry. There are many drugs in the market now to combat these diseases that are traversing the system. And I think that my dream to understand the reasons of diseases came true in a way. If you remember, in medicine, you are learning how to treat a single patient. But via science, I think that the road was opened for me to impact the lives of millions of people worldwide. But these drugs that are being used all over the world, including in Ecuador.
Thank you, Aaron, for your explanation. And Rich Roberts, I would like to ask you the same question that I mentioned before to all the colleagues.
Okay. I got interested in science because my father bought me a chemistry set when I was about 11 years old. And it was rather simple experiments that you could do, change color and so on. But then I realized, after reading a little bit, that I could make fireworks with these compounds that were in my chemistry set. And, you know, just like I understand all these terrorists, they really like a good explosion. And for me, this turned me on to chemistry. Before that, I thought I was going to be a mathematician because that was what I really loved when I was about 6 years old. And then I read a book about being a detective, and I thought that sounded pretty good too. But chemistry really captured me because of fireworks. And I went to university, did chemistry. And in the last year of my PhD, I read a book by John Kendrew, which it was called The Thread of Life, and it was about the origins of molecular biology. And so by the time I finished that book, I knew this was what I wanted to do with my life. So I applied for postdoctoral positions that would allow me to learn something at least about molecular biology, even though I was an organic chemist. And I got accepted by a guy in Wisconsin called Jack Strominger. And about 2 months before I was due to head to Wisconsin, he wrote to me and he said, well, could you delay for a little while because I've just been appointed a professor at Harvard. And so I ended up, quite by chance, going to Harvard to do my postdoc. During that time, I learned how to sequence RNA, which I thought was really pretty cool at the time. I went to Fred Sanger's lab. Fred Sanger, double Nobel laureate, wonderful guy. Then Jim Watson heard about me and asked me if I wanted a job at Cold Spring Harbor, and so I went to Cold Spring Harbor. And I started doing a variety of things there, pretty much everything that Jim didn't want me to do, and nothing that he wanted me to do. But nevertheless, it's been the story of my life. I always think if someone tells me you should be doing this, it's probably not that interesting because they thought of it. But if I think of it, then I think it's worth doing, even though other people say you're wasting your time. And so we started to look at adenoviruses. These are small viruses. They cause, complications, not often. Usually it's just the symptoms like a cold, and you get it when you're very young, you get antibodies, and you're immune for the rest of your life. It essentially becomes a vaccine against this virus. And we were interested in what was a promoter, something that tells a polymerase, an RNA polymerase, where to start making messenger RNA, i.e. where does a gene begin? And we wanted to know if the signal was the same in bacteria as it was in higher organisms. And so we chose adenovirus, which grows on human cells, to do these studies. And I had a postdoc, Richard Gelinas, and I gave him the experiment, and I came up with this wonderful way of doing it. It was really a cool technique. And I told him, you know, do this experiment. We're going to get some great results out of it. And he did the experiment, and of course it didn't work. And so I said, go back, do it again. He did it 2 or 3 times, got the same result. I said, you know, just sit down, let me do it. I'll show you how to do it properly. I did it and got the same result. And I think from this, we learned something that I'd sort of vaguely known before, but it really showed me very seriously how failure is one of the best things that happen to you. Because when you fail, if you look back and ask, why on earth did this fail? What went wrong? And you can find out, then you discover something, then you learn. This is true for businessmen as much as it is for scientists. Most businessmen start a business, it doesn't work, they figure out why, and then they go on and are successful. So in our case, we wanted to know why this experiment didn't work. And the answer, without going into all the technical details, is because transcription and the making of messenger RNA in higher organisms, humans, plants, and adenovirus, is different from the way that it happens in bacteria. What happens in bacteria is a gene is just a linear piece of DNA. You start at one end, you copy it into RNA, that goes to a ribosome, and then it makes a protein. Very simple. And you read the messenger RNA 3 bases at a time. It's not like that in higher organisms. In higher organisms, you first make a very long piece of messenger RNA, which contains bits and pieces of the real gene in it. And it is only after this very long transcript is cut and spliced in exactly the same way that a Hollywood producer makes a movie, where you shoot one scene and then another, and you cut and splice so that you eventually get something that looks as though it's continuous. This is how higher organisms make their messenger RNA and then make proteins. And this was such a fundamental difference from the way that bacteria do it. And at first, you know, we had some problems. People didn't really believe it, but eventually they did believe it. And eventually, this led to the Nobel Prize in 1993. And so it was just a wonderful discovery to make, because it was really very basic. You know, it was like the discovery of DNA was a big deal. All of a sudden, here was the secret of life. Well, the study of messenger RNA, how it was made in higher organisms, meant that now that we have the human genome sequence, we can understand how it is translated into protein. How is it that this sequence eventually makes proteins? And so for us, this was really wonderful. The day that we did the very first experiment that proved it, in 1977, people were talking about Nobel Prizes. But for me, the lesson I learned was that luck is really important. This was a lucky discovery. And the nice thing about doing science is that every time you make discoveries, they may be small, they may be big, experiments fail, you work out why, you have the opportunity in order to learn something really big, and you never know when this is going to happen. And so for me, I feel immensely lucky. I can give you many more examples of that if we talk privately. But this was a wonderful discovery to make, and has laid a basis for understanding how higher organisms, how the DNA is organized, and how it leads to the proteins that make us work.
Richard, it's your turn to explain to the audience about
Thank you. Rich Roberts has stole some of my thunder, because I got a chemistry set when I was 8. So I don't know, I guess among the 4 of us, I win the prize. Okay, so that's how I became interested in chemistry, because chemistry, it was given to me by my older brother, who went on to be a very successful surgeon. He went into medicine. And I had a brother even 10 years older who became an engineer. I'll talk more about my family origins in my talk this afternoon. But what happened? Well, I became interested in making fireworks, figuring out, you know, why acetic acid and sodium hydroxide react with each other, and so on and so on. And did experiments. I set up a little laboratory, much to my mother's dismay, although she actually helped me a great deal and encouraged me, and so did my father. Even though they did not graduate from high school, they were removed from school for religious reasons and put to work on the farm. So they were angry about that, and they, I think, put their anger into me and my brothers to succeed through education, which I ultimately did. So I would say the most interesting time in terms of why I ended up where I ended up is when I got a job at DuPont, which Jose mentioned. DuPont at the time was a leader in doing research of potential interest to making more money, of course. And I have received an interest in organometallic chemistry, so I'm an inorganic chemist. You've heard a lot about organic chemistry, but I'm an inorganic chemist, which basically is all the other elements in the periodic table. Now I think we're up to number 118. And I like to make things. So that's how I learned at Harvard that I was not a physical chemist. I like to make things. I like to crystallize. I like to do things that I learned when I was 8 years old. And I didn't get a job initially, ended up at DuPont and began basic studies in organometallic chemistry. Now, organo means carbon, usually there are other elements, but metallic means obviously metals. So these are really directed towards the synthesis of metal-carbon bonds. Single bonds, you can have two bonds, a metal double bond to carbon, or a metal triple bond to carbon. At that time, there was a reaction that popped up, and that's what happens often in science. Things are discovered that can't be explained, and a lot of people in various fields sometimes became interested in what was the explanation? How? Why? When? Where? How to solve this puzzle? We can solve puzzles through science. I learned that, and I didn't set out to make the discovery that I actually made at DuPont, but in 1974 I did learn how to make metal-carbon double bonds, which were of interest potentially, although none were known at the time, that particular type, in a kind of reaction that was discovered in, depending how you look at it, about 1964 or even in the mid-50s. And ultimately, I moved to MIT in 1975. I only spent 3 years at DuPont, and I wanted to go back into academics. I wanted to solve this problem since I learned how to make this wonderful new family of compounds, these catalysts for a reaction that turned out to be, of course, an organic reaction, and that is chopping up carbon-carbon double bonds and redistributing the pieces that alone don't exist, because they do many other things, to give products, other ones containing carbon-carbon double bonds specifically. So that turns out to be the metathesis reaction. Metathesis means switching places. So you take these carbon-carbon double bonds and you switch the ends and make new products. So in 1975, I moved to MIT. I learned how to make other catalysts, the ones that actually do the reaction naturally, that contain molybdenum or tungsten. You have to go to your periodic table and find out where those are. I'll show you this afternoon at my talk. And develop the chemistry, apply the chemistry. I mean, we've been talking, all of this is applied chemistry, applied to biology, applied to physics, applied to medicine. Physics, I tell my wife, everything's either chemistry or physics, and sometimes both, as you heard. So I had the advantage of collaborating with organic chemists, because I'm not an organic chemist. I make the molecules that do organic reactions, and for that I received the Nobel Prize in 1975 with a man named Yves Chauvin, who was the first one to write down the mechanism of the reaction, which involves a metal carbon double bond reacting with a carbon-carbon double bond to make a ring. And Robert Grubbs, who developed similar catalysts to the naturally occurring molybdenum and tungsten catalysts that contain ruthenium. He was an organic chemist, and myself. I had collaborated with a man named Amir Hoveda for 22 years now. I've collaborated and applied the chemistry I'd learned. He applied the chemistry I'd learned about and developed catalysts for to the synthesis of new molecules, and that is continuing today. The one thing that, so in 2005 then the prize was awarded, but there were many unanswered questions, and there was one big unanswered question when I moved to University of California, Riverside now, where I am part-time, and that is, where do these molecules come from naturally? Because they can occur naturally. Nature makes a lot of things that you would not believe, of course, could be useful, and she controls them, of course, free radicals and all sorts of crazy reactive molecules. And it turns out that the most basic metal carbon double bond, a metal CHH, is made by nature naturally. It was discovered only a year ago and has been an unanswered question for roughly 60 years. And so I'm very pleased to have finally found out how nature does it naturally. And I'll talk about that this afternoon. And this sort of work is a different field than what you've heard about, but it is applied to organic chemistry, and that was actually the statement that the Nobel Committee chose for contributions, my contributions to organic chemistry is why I received the prize.
Bien, y antes de dar paso a las preguntas que van a hacer estudiantes del público que nos acompañan, a mí me gustaría hacer un comentario sobre lo que hemos oído en este rato. Y lo que hemos oído son varias cosas, y esta me dirijo directamente a la audiencia joven que nos acompaña. Hemos oído que la ciencia es divertida. Hemos oído que la ciencia es un reto, porque hay cosas que buscar que nadie ha encontrado y que por tanto automáticamente se convierten en algo interesante. Hemos oído cómo la ciencia, los descubrimientos son producto del esfuerzo y de la suerte, como decía Rich Roberts, aunque para tener suerte hay que buscarla. Como decía Pablo Picasso, está muy bien tener inspiración, pero es mejor que te encuentre trabajando. Entonces, hay que esforzarse para ser proactivo en aprender, en formarse y sobre todo en buscar lo que realmente hay oculto en la naturaleza. Y hay tantas cosas aún por saber y por descubrir que a mí me encantaría que al menos una persona de esta audiencia, después de este día, decida que quiere ser un científico, que quiere buscar la verdad oculta en la naturaleza, y que la motivación que estas cuatro mentes brillantes que nos acompañan les hayan dado hoy sirva para que al menos una persona de esta magnífica audiencia decida que efectivamente vale la pena ser curioso, ser interesado en buscar lo que la naturaleza nos oculta y sobre todo divertirse haciendo ciencia, porque yo que les conozco muy bien a todos ellos, puedo decirles que se lo pasan estupendamente haciendo lo que hacen. De hecho, con Rich Roberts he tenido alguna conversación cuando digo, no paras de trabajar incluso en los aeropuertos. Dice, no estoy trabajando, estoy divirtiéndome, estoy haciendo lo que me gusta. Así que, por tanto, a mí me gustaría que esa fuera la principal lección que ustedes sacan de aquí. Entonces, no, dicen que no han recibido traducción simultánea de esta parte. Bueno, pues entonces ahora vamos a dar paso a las preguntas de los diferentes jóvenes que quieren hacerles preguntas a ellos. Now we have the questions made by the young students who will address the question to you.
Hello, good morning. Hello.
Yes,
Well,
we can see you.
My name is Amelia Arcos. I am a student at Cómo, and my classmates and I have prepared a question that we would like you to answer. Yes, so Richard Roberts, well, considering introns are discarded in eukaryotic organisms, why hasn't evolution or in time completely eliminated them? And well, why do they still, how are they used in prokaryotic organisms?
Okay, well, that's an interesting question. If you look at some of the lower eukaryotes, like yeasts, they have eliminated a large number of these introns. In fact, for people who don't know, introns are these regions that are present within a higher organism's genes that separate the coding parts from the rest of the gene. So these introns, they clearly are playing a role. And there are good examples in some cases where they are controlling the expression of genes. But for the most part, we have absolutely no idea why they're there. It may be that because a mechanism has evolved to get rid of them, that is RNA splicing, the mechanism of editing these messages, that it is difficult now to get rid of them, but that doesn't seem like a likely explanation. And so I think most of us who think about this believe that what is going on is that there are lots of things they're doing by way of regulation, or because of their importance within gene expression, or the fact that they can allow alternative parts of genes to become joined to make different versions of a protein, that they do actually play a very useful role. And the guess is that the reason we don't see them in bacteria is bacteria have to grow much more rapidly, and archaea too have this. They grow much more rapidly on the whole, and they have simplified everything that they possibly can. But the eukaryotes, I think if we lost our introns, we'd be in big trouble. But the bottom line is that for more than 90% of the introns, we don't know what they do. Here's an opportunity for some young scientists to come along and make some big discoveries. And maybe that would be a route to a Nobel Prize.
Next one.
Good morning. My name is Diego Mayorga. I study at Academia Naval Guayaquil. I would like to make a question to Richard Schröck. Richard Schröck, good morning. First, I want to congratulate you for your Nobel Prize, and thanks to visiting my country. My question for you is, how do you feel to being here, to be able sharing with us about your career and how it feels to be one of the leaders on the chemistry area?
Let me try to figure out exactly what you have asked me. Could you repeat that or have a translation, Jose? Repite, por favor.
How do you feel to be one of the leaders in the chemistry area?
How do I feel? I feel great. I think it's... No, everybody wants to be recognized. I don't think we would be human if we didn't want to be rewarded for something we do. But you know, you have to, it has to happen naturally. You cannot demand it. You cannot order it like pizza. You know, you have to let it choose you. And that's more or less what I did for me. It chose me somehow. And, or I let it choose me. I don't know. It's very difficult to describe. I don't know the answer, but I do feel very happy to have been rewarded in that way, and to have been rewarded with a Nobel Prize. I never dreamed of a Nobel Prize. I never knew what a Nobel Prize was when I was very young, of course. But it is obviously a tremendous recognition, and I feel that now maybe I can give back to people like you something to inspire you to, whatever that something is, to inspire you to not seek a Nobel Prize, but just do something that makes you happy and that you enjoy. You can make some sort of living and to seek to do the best you can through whatever gift you are given. And I think science is an important gift, and I hope you use science to do that.
Good morning. My name is Romina Brito. I'm here, over here. Sorry. I'm from Javier School, and I guess this is a question for all of you. We have noticed that in our research process, at some point, we reach a moment where everything is absolutely new. So this is a moment of complete uncertainty. How do you know that what you're doing is whether correct or not? And what did you do to get out of this moment of uncertainty? Thank you.
Anybody? I like the way you heard some words in Professor Roberts' presentation. One of them was cool. The reason why a lot of what we do what we do is because it's cool, and that means we think that, well, we obviously like doing something. It's new, we think, but we don't think about the future too much. We like to do on a day-to-day manner something that makes us proud, makes us proud of ourselves and what we know. And so I think that it's something that you have to, I always say that, as I said before, chemistry chose me, or I kind of fell into chemistry. And that's what makes me happy. And I think I'm very, of course, happy to have been rewarded in some way ultimately, but that's what keeps me going from day to day, because it's cool to make discoveries.
Yeah, it's a very interesting question, and all of us are facing these moments of uncertainty. I think that the problem for you is much more complicated than it was for us. I think that I grew up in a very simple world. There was no Twitter, and no Facebook, and no social media, actually no television, and certainly not this little machine called cell phone that everybody is busy with all the day long. But nevertheless, for myself, as you heard, I changed my career in the middle. I was already an established physician on the way to become a surgeon, and I decided that this is not for me, that maybe my mother wanted me to be a physician, but I didn't want to be a physician. But it took me a long time to realize that, and nothing happened. Actually, what I'm doing now is tightly related to medicine, though it's not practicing medicine with patients. So I think that you should know where you are. I never wanted to be a ballet dancer or an architect, so I was already on the side of biomedicine. And then it was a matter of choice, and then you can change. Nothing will happen. You know, the average lifespan now has extended enormously. People are living now 80 and 85 years. There is a lot of time to get bored, and change is just fun. You know, you are taking your experience from your previous career and you are bringing it to a new career. I think that I have a very peculiar philosophy of life. Life is not about achieving something particular, because once you achieve it, what you do next? And then once you get the first $1 million, what you are doing, you get the second and the third, and then 99% of it you are leaving behind you once you are leaving the world. I think that life is about a chain of experiences and enjoyable experiences, and you are moving from one to another. So I don't regret for a minute the 15 years that I spent in medicine. Not for a minute. It gave me a lot. Though I'm not practicing medicine anymore, I took the lessons and applied it to biochemistry and molecular biology, and now actually I'm doing something completely else. We are in drug development based on the system that we learned. We have a company with investment, and we are very close to clinical trials. I will talk about it this afternoon. So it's an experiences that you are just moving from one to another. So it's legitimate to have moments of uncertainty. You can live through it, change if you don't like it, and move on.
The other side. Erwin?
Can you hear me? Yes, yeah. Well, I can just agree. I mean, you have to deal with failure in your experiments. You have to deal with multiplicity of problems, you know, but you think about your problems and you enjoy then finding answers, you know. So it's in a way a circle, but I think trying to understand the situation where you are in helps and will in the end bring you one step further.
I always think that there are opportunities to do all sorts of different things. And I very much encourage people, if you're in one field, read about other fields, read about other stuff, because you never know when you're going to come across something that is more fun than you're doing at the moment. And if you read about it and think, hey, that would be fun, don't hesitate to switch. So what I do these days, I actually do bioinformatics. I look at DNA sequences. I use computation. In fact, many years ago, I wrote the very first programs for putting sequences together, for determining complete DNA sequences for things. Nowadays, I look at my laptop or whatever instrument I have in front of me, as Aaron would say. I'm not a big fan of Twitter. I'm not keen on social media, but I do like looking at sequences using the computer. And I would say every day I make a discovery. I don't care whether it's a big one or a small one, just the thrill of seeing something for the first time that no one's ever seen before. You can't beat it. It is just fantastic. I used to go underground in caves, looking for new passages, looking for areas that people had never been before. And this is great. It is such fun. So I see today, with all of the uncertainty that is around, I just see opportunity. Here is an opportunity to find something that you will enjoy doing, maybe something that will be good for humanity, for the rest of us. That would be good too. But I feel unbelievably lucky that my early love of mathematics, this idea of becoming a detective and then learning about chemistry, and now I do bioinformatics, everything I've ever loved doing in my life, this is what I do every day in the lab. And I'm sure you too can do this. Something that you love to do.
Tenemos algunas, sí, hay un señor al fondo, pero después había algunos estudiantes que tenían preguntas programadas. Sí, ahí, sí. A ver si lo vemos.
Good morning. My name is Audrey Angulo. I'm a student from Mercedes School. My question is for Sir Richard Roberts. Since you won the Nobel Prize, you have been involved in the organization of different initiatives to correct scientific misunderstandings. What types of confusions have you corrected to date, and which of them do you consider to be the most serious?
Okay, well, it's true. One of the things I discovered after I won the Nobel Prize is that I would sit, stand, talk to people, and all of a sudden they were listening in ways that they'd never listened before I won the Nobel Prize. It basically gave me a bully pulpit to talk about things that I thought was important. And I've run a number of campaigns. People sitting here with me probably always hesitate when they get an email from me as to whether this is something else I'm going to ask them to sign on to and help out with. But we've actually had some success. We were able to get a bunch of nurses, some Bulgarian nurses, out of prison in Libya who'd been accused of spreading AIDS around. That was very successful. We've done a number of other things that have been less successful. Sometimes people listen, sometimes they don't. But what we found, and what I found, is that by organizing Nobel laureates, get a lot of people to sign on to something, this will encourage other people, very often governments or officials within governments or within companies, to do things that they otherwise might not have done. And I think this has been something very successful. At the moment, We have a big anti-GMO movement, that is a pro-GMO movement, which I will talk about later this afternoon. But there are other things that we're trying to do also. And in general, what we've tried to do is to support humanitarian causes, to do things that are good for people, and also to correct scientific misunderstandings, which is really what the GMO campaign is about. We obviously need also to correct misunderstandings about vaccines and about other aspects of medicine. And perhaps this is something that we should get a lot more involved with as Nobel laureates. But again, I usually do things either that I've found to be interesting or that other laureates have asked me, would you start something here, would you start something there? And I think this has been a good thing, and it is also something the Nobel Foundation is getting quite interested in supporting as an organization. And I'm going to meet with the head of the Nobel Foundation later this year to discuss ways in which perhaps the Nobel Foundation itself can get involved in taking advantage of those people who become Nobel laureates and have this holy pulpit where people listen.
Tenemos algunas preguntas más de nuestros jóvenes, porque antes, sí, por ahí, es que yo antes de dar la palabra a nuestros adultos, prefiero dársela primero a nuestros jóvenes que tienen pocas oportunidades de esta historia. Así que al señor que está al fondo, al final le doy, pero prefiero primero que nuestros jóvenes puedan tener opciones de preguntarles a ellos. Así que, si pueden, por favor, sí.
Do you hear me? Okay. Thank you. Erwin Neher. Yes, this question is for you. I do not know too much about chemics, but I found interesting you mentioned about ions transfer of sodium and potassium. I'm right? Oh, yes. I'm nervous. There is a correlation between the quantity of ions and how our brain reads the message. And if there is some kind of disease, pathological disease, that can affect how these ions interact with each other. Thank you.
Well, I'm sorry, I didn't hear part of your questions because suddenly the channel here switched between English and Spanish. So I try to answer the last sentence of your question, which I think was about the relationship between but maybe you can repeat it. I'm really sorry.
Between quantity of ions and how our brain intercepts the message.
Between quantity of science?
Ions.
Ions,
yes.
Ions. Oh, of course, this question bridges a large level of large range of levels, you know. I mean, the ions which flow determine the electrical status of individual cells, you know, and as the very original question which was on my mind about how the action potential gets generated, we know now it's a question of ions flowing in and out and creating action potentials. And now this is the basic level. The next level is on the level of cells, how cells interact with each other, you know, and this is with regard to nerve cells, it's the synapses, the places of contact between different nerve cells, and this creates a kind of pattern of activity within a group of neurons. And then you have the very high level, how the system as a whole behaves, how it tries to predict on the basis of sensory information what's next, how your body has to respond to, say, when walking with certain hindrances on the way. That's a job of really creating a kind of representation of the world around you within yourself, you know. And of course, this level is based on very different principles than the low level of ions, which just make signals pass between within a cell and between individual cells. So, I mean, you have the different fields of neuroscience, the molecular neuroscience, the cellular neuroscience, systems neuroscience, computational neuroscience, which then tries to explain how neuronal circuits work, how they interact with one another, how they generate certain rhythms, and so on. So, I mean, depending on what kind of questions you are interested in, you can study this phenomena on different levels. And my work started with the lowest level, you know. Now for the last 10, 20 years, I have switched one level up, say, the problem of synaptic transmission, but on each level you find different laws, different concepts which describe what you are seeing.
Good morning to the audience present. It is a pleasure for us to attend this event. We noticed in Dr. Richard Roy's and Dr. Aaron's profiles that you studied philosophy in the university. So we came up with the question, to what extent do you consider that every scientific research and reflection should go along with a philosophical one?
So just repeat the question. What?
To what extent do you consider that every scientific research and reflection should go along with a philosophical one?
Oh, yeah, okay, philosophy, yeah, philosophy. I believe that you shouldn't rely on a rule like that. What we've been talking about is being interested in science, being interested in solving puzzles, being interested in solving the puzzle and benefiting yourself and mankind and whatever it might be. I must admit I don't really understand why the question came up, because philosophy is a discourse. It's not really a science. So, and there is such a thing as a philosophy of science, I guess. But I think when you talk about science, I mean, it has its own rules and reasons for doing what you do, and I think you've heard a lot of them up here. Since philosophy is a discourse, I really can't say that I would insist on following any philosophical direction in science, at least not my science. I hope that helps.
So,
to relate to it, I may not believe that science does need real philosophy in order to move forward. But in medicine and in biomedical science, there is one aspect of philosophy that should be an integral part of the science, and that's bioethics and ethics. It's really an integral part of science, and we should not ignore it. And I can bring you a few examples. Let's talk about abortions and the end of life. You know, abortions on one side and the end of life. Can we take the deliberation, can we, to end life of people. There is a huge discussion on it because it has also an economical issue. How much it takes in order to maintain a patient in an intensive care unit that everybody knows has no chance of recuperating and getting back to life. So this is, for example, the issue of vaccine that was mentioned by Rich Roberts. We cannot enforce people, but is it, can a society enforce people to get vaccinated in order not to risk others, or should society leave it to the decision of the people to decide what they want to do or do not want to do, despite the fact that they might risk people? And I can bring many other issues about it. There was an issue just with the COVID-19. Luckily in Israel we didn't have it, but in Italy and in the United States, they faced it. When you have more patients that need to be put on respirators versus the number of teams and equipment that you have, whom you are going to put on the respirator and whom you are going not to put on the respirator, and by that basically, decide that this patient is going to die. How you make a decision on life and death. So this all have to do with human beings, it has to do with ethics, and it has to do with science. So I think that this part of philosophy should really be part of science.
I would agree totally with that, that for me, a lot of philosophy is not something I want to spend a lot of time on, but ethics, I think, is incredibly important. And as scientists, I think it is important that we realize when we make discoveries or when we're developing new techniques, which is the way we often make new discoveries by developing new techniques, new ways of asking questions, that there can often be ethical considerations that are quite important. And I think one of the prominent ones at the moment is our ability to edit genes, to edit the human genome in particular. And should we be doing this? And if we should be doing it, under what circumstances? Or are there circumstances we shouldn't be doing it? And there was a case not too long ago of this Chinese physician who obviously thought this was his way to get a Nobel Prize, was to gene edit a fetus, and it was unnecessary. It was just a showcase in the hope that he would gain some prominence. But there are diseases that for sure we can help. And I think things like sickle cell anemia, which is something that we can do on blood cells. It doesn't involve necessarily doing gene editing on an embryonic cell. It is something we can do on somatic cells. This sort of thing, when it can cure an illness, I think this is something that we should do, but we should make sure that when we do it, we don't do a lot of things, we don't do a lot of damage as a result of doing it. And so these are the kinds of ethical questions that Aaron is referring to. And I think these are important, but I'm not sure the other philosophical questions are one I want to get involved in. But ethics, absolutely, very important.
Erwin, do you have any?
No, well, I agree that ethics is very important, but I ask my question, can we develop ethics on an issue which is not within the range of experience of everybody, How to develop ethics, say, on the question how to deal with a blastocyst, or a very early embryo, which you can observe only under the microscope. Nobody has experience with what such a structure is like. How can society develop ethics on this? And I think it simply cannot.
Thank you very much. ¿Había alguna pregunta por ahí de algún estudiante que me habían dicho que tenía? Sí, ahí.
Yeah, hello. My name is Nicole Silva. I am studying chemical engineering right now, and I am a member of ESPOL. And I was wondering, this question is directed towards Dr. Richard Royce. I was wondering if the reaction involving the organometallic catalyst is stereospecific, because sometimes when the direction of rotation or change in structure of these molecules can make the molecule hazardous.
There we go. So you're really asking, how do you make catalysts do what they do? And many people think that, oh, you have one catalyst that will do whatever you want. But no, the catalysts are very specific, and they depend whether it's in biology or whether the kind of thing I do, the things you put on the metal that direct and influence how that metal-carbon double bond does what it does, in what turns out to be a very complicated way in terms of decomposition or propagation, or, as I'll talk about today, regeneration of the catalyst and so on. It's very dependent upon the local environment in the catalyst of any type. So it takes, of course, there are many, many variations, not an infinite number, but a very large number of variations. And it takes a long time to evaluate all of those variations to see and understand how the reaction works. And I must say, we still don't have complete control and complete knowledge in terms of all the possible variables, how to completely control a reaction and get the result we want. And so that's why research in my particular area, and probably other areas of catalysis, continue. So you have to study variations and understand as much as you can, all the possible steps of creation and destruction and operation of a catalyst in a given reaction.
¿Hay algún otro estudiante? Sí, ahí había uno, sí. Porque de hecho estamos a punto de terminar, pero a mí me gustaría que no se quede ningún joven, que era básicamente para quien iba dedicado este evento, sin hacer las preguntas que estimen oportunas. Porque los adultos tienen siempre oportunidades de hablar, pero los jóvenes no tantas. Así que me gustaría que no se quede ninguno de ustedes sin hablar, y ya que nos queda muy poquito tiempo, por favor.
Good morning, my name is Sofia Mejia. I'm from Mercedes School. This question is to Dr. Aaron Ciechanover. In various interviews, you have praised your tutor, Abraham Hershko, and the great influence he has on you. How is your relationship with him today? And now, you as a tutor, what traits did you adopt from Hershko, and how do you differ from him?
You know, Avram was my mentor, and he was a superb scientist. He's still a superb scientist. He's working next to me, a few floors below, so we are still in the same building. And he had a different approach to students than I had, but on the other hand, it fitted me because I came from medicine. And when I came from medicine, I didn't know anything about science. Well, I knew a little bit from what I remembered from medical school, but this was very little. I couldn't operate the pH meter, I couldn't operate the centrifuge, I couldn't do anything. And Avram took me by hand, step by step by step, like I was a first grade beginning student, and he showed me the way to science. Then I came to MIT, and MIT is a very different institute. I was in the laboratory of Harvey Lodish, who is a superb cell biologist, but at that time we were about 40 people in the lab. About more than half of them were postdocs, and about quarter or 12 were graduate students. And he didn't have time for each of us. And it was a hard time for me to adapt, to become completely independent. Harvey was, again, an excellent teacher. And he was interested in the results, but once you had already carved the story. He was not into teaching us the details. But so this was a different type of a school for me. So you see, I was educated by two different teachers. Each of them had his own advantages. I somehow adapted in my laboratory the approach of Harvey Lodish. I give the students the opportunity either to swim or to drown. So I'm helping them. You know, we have subjects in mind, we are discussing it. I'm helping them to get, of course, the funds. I bring the funds to the lab. I'm writing the grants I'm being helped by the students. But if they cannot do it on their own or by consulting their peers or by crossing the corridor and go to some other lab and ask for help, then, you know, I cannot help them. The idea is to really help people to develop as independent scientists. And me, I was maybe an exceptional case because I really came from a field. You know, if you look at medicine, surgery is the farthest away from science as one can imagine. I was not in cardiology, I was not in hematology, I was not in internal medicine, I was in surgery. So it's really a very manual type of a profession, and I really needed the help of Avram. But I adapted a different approach to science, and I'm lucky that I have had and still have very good students that made it to independence and to occupy senior positions in both academia and the industry.
Thank you. Bien, me indican que ya para finalizar tenemos dos preguntas del profesor de la ESPOL y de un estudiante, así que por favor.
Hi, my name is Carlos Gonzalez from the Faculty of Arts, Design and Audiovisual.
Sí, mejor.
Thank you. So, well, my question is, I think, a little bit complicated, but we live in a multidisciplinary world. And I would like to know what you think about how do you consider the relationship between science, the arts, and design could be. Thank you.
Sorry, can you repeat?
My question was, we live in a multidisciplinary world, and I would like what do you think about how do you consider the relationship between science, the arts, and design could be?
The relation between science, art, and design could be. Someone could reach.
So, I have no expertise in this area, I'm glad to say. My wife is an artist, and so we often talk about these kinds of issues. But we actually have a guy who works at New England Biolabs who makes art with bacteria. And so he grows bacteria, makes incredibly interesting designs. He works with an artist himself, but he has a lot of art and a lot of design in his background. I'm just using bacteria to do interesting things. And so there are opportunities for this, but they're few and far between, at least as far as they've been exploited at the moment. Another aspect of this is when we're trying to make presentations to the general public. It is really useful often if you have a good designer who can help you to design slides, can help you to make PowerPoints that are very illustrative of a particular point and done in such a way that you don't need to be a scientist to understand them. And I think this is something that we actually fail at quite often when we're teaching science to young students. We often do not give them the skills, we don't teach them the skills of communicating to the general public. And I think this is a fault that many of us have. I always felt lucky because I grew up in England where we were forced to present to our fellow students on a regular basis and explain to them what we were doing, what we knew, what we had read about in ways that could be understood by the general public. And there are a few universities these days. I notice the university in Zurich is very good at this. They actually make their students go out onto the streets and talk about what they're doing. University of Exeter in England now does the same thing. But I think we really do need to teach scientists how to communicate to the general public. And this is where art and design really can be very, very helpful.
Aaron?
Well, since we are all human beings and we are very curious, all of us, so of course science and art and other areas are linked to one another. So we are enjoying music. Now we are in Ecuador. Part of traveling is curiosity. We are going to the Galapagos to understand what Darwin did see and what conclusions could he draw. He was a genius, there is no doubt of it. So we are enjoying the world around it. We are not limiting ourselves to science. But the question is how to really link it. Whether, understanding art is essential for understanding of a success in science. And this is a little bit more difficult. All I can say from my own personal experience that it's enriching. And recently I was contacted by several artists, and they had a project in mind. And the project was really to link science and art. So they told me, let's discuss it. And we spent many hours together. And then we came to some kind of a conclusion that turns out to be successful. So the idea was, at least for me, that we took the molecule that we discovered, the ubiquity molecule, and one of the artists made an artistic illustration out of it. So nature is clearly the best artist. There is no doubt about it, at least in my opinion. Just see the beautiful bacteria that are growing as part of this artistic project that Rich was mentioning a minute ago. So we took this one and he said, okay, so what are we going to do with this ubiquity molecule next? So we decided to put it on an electronic board. And the electronic board behind it has many letters. And the letters were organized according to the computer organized it. How did the computer organize it? The artist told me, make some statements of what you think, very short statement. So one of the statements that I made, of course, that when you look at the ubiquity molecule, you cannot escape the conclusion that nature is the best artist. The other thing is, and there are many statements like that that I made. I composed 25 sentences. The 25 sentences were fed into the computer, and the computer made a collection of letters. And now what happens, and they put a chip behind this frame with the ubiquity molecule, and every few minutes, one of my statements is lit up with lead letters, and then it turns off. Then you keep on waiting, and after a minute, another statement is lighting on, and the other statement can be, the best treasure of a country are the brains of its people. And I made 25 like those. I must admit that they might not be all original. Some of them were stolen in one part or another from Albert Einstein and from others. Well, you cannot invent the wheel all the time. And we made it a piece of art. So the piece of art is the ubiquity molecule, and behind there are statements that are being lighted on and off, and you can stand next to it for an hour reading all of those. So the company decided to make business out of it, and they are selling each of them. They sold a lot already. Of course, I'm enjoying a small share of the earning. And then they decided to expand it. They went to physicists. They went to the Hebrew University in Jerusalem, which owns the intellectual property of Einstein. Einstein inherited all his intellectual property, even the name, to the Hebrew University. So you cannot make tomorrow a shirt. Well, you can, but that will be kind of robbing an intellectual property. You cannot make a shirt and make money on it by putting the name of Einstein and one of his statements on the T-shirt. Only the Hebrew University has the rights to do it. So they went to the Hebrew University and they bought some of the rights of Albert Einstein, and they put his famous picture with his tongue out and his famous statements on it, and so on and so forth. So this shows you, at least I don't say that it's that art is essential for science, but the way that art and science can interact for the benefit of the public.
Very much.
La última pregunta, antes de cerrar este evento, le corresponde a la dama que en este momento está de pie.
Thank you. Hi, my name is Juliana Gajardo. I'm a biologist study from here, ESPOL, and me and my friends have a question for any of you. It is a fact that you all form yourselves as professionals in developed countries, or at least more developed than ours. So sometimes it is difficult for young people like us to imagine working and living of science because we don't have much support for this kind of careers. In this context, what could you recommend us in order to achieve a successful career like yours?
What would you like to answer?
Well, I mean, for me, the question whether you can be a good scientist is whether you can identify a problem which really captures your mind, you know, and if your mind is set up in a way that you want to solve this problem. And if your mind is set up in this way, then it doesn't matter whether you live in a developed or less developed country. Of course, in a more developed country, you have more local possibilities. But if you really want to be a scientist in the sense that you are curious and want to solve a problem, you should just go for training, for trying out your abilities into some other countries. I mean, I think in Germany, a good scientist is expected to have, I mean, who wants to become a professor or so, is expected to have spent at least some time outside your country, you know? And then you have to see how your path, where your path leads you. Does it lead you back into your country because you have acquired skills which suddenly allow you to formulate questions, to formulate problems which are important for your country, you know, or else whether you are just concentrated on your a problem and find out that you can better solve it in some other country.
So one of the things that you can do is to take advantage of the internet and the possibility for learning through the internet. For instance, MIT makes many of its courses available over the internet, and so you can learn in this way. And I often think that many of the best students actually teach themselves to a large extent. They read books, they see what other people are doing, they start to think about questions that they might ask, and many of them email me and they ask me questions. And I've had a number of students. I had one fairly recently from Peru who had contacted me some 15, almost 20 years ago. And I'd been having occasional emails with him. And he is now in Holland, in the Netherlands, doing research. He's a research professor there. And he credits me with having helped him out. I don't think I did very much. I think it was mainly him. But it's surprising what you can do if you're resourceful, you know. So you have to really want to do something, have some good idea of how you might get involved in it, read as much as you can, and then use the internet in as many ways as you can to help you further your education and reach out to people. You'll be surprised at how many people will answer you when you write to them in a polite way.
Do I have any comments? No, I think these are all good comments by others. You cannot be trained completely, I think, anywhere except maybe a few countries here and there. But in general, I mean, you have to be trained, as the first comment made, brought up, you have to be trained well. You have to learn as best you can, given the resources you have in your home country. If you can go on, you've developed some interest. If you can go on, whether it's in an area that's not represented elsewhere, maybe some ecological chemistry or chemistry of the environment that requires that you stay in your country, fine. But you should be trained in other approaches and find what you want to learn, search out. Very often everybody here has searched out one way or another the person that really is best in the area. And that often means you have to go to another country. But we're a global scientific community now. I think you can see that and have heard about it. So it's up to you to receive your training, decide what you want to do, and then pursue it one way or another. And very often that means moving to a lab outside of your country.
So people talked already about, I would say, an essential fundamental requirement to leave your place and to go elsewhere. It's certainly true for Ecuador, like it was true for me in Israel. It's a small country, everybody knows everybody, and I needed to go, not that it was required by others, I felt that I need to be exposed to a different type of science, to a different language, to different culture, and I went probably to one of the top people in the world, certainly to one of the top institutes in the world, to the MIT, and these were very rewarding. But now comes the question, are you going back to your country? And this is a major country, and for sure, Ecuador needs experts, like Israel needs experts. I considered a lot. I had many offers in the United States, and I was tempted, I must admit, to stay in the United States, but at the end of the day, I made a decision to go back. And the decision was based on the fact that Israel and my institute prepared the background for me for coming back. They helped me to build my laboratory. They provided me with a very generous startup funds, equipment, technical help, fellowships for graduate students, and so on and so forth. So I felt that I may sacrifice something about, I might have been more successful staying in Stanford or Princeton, but in Israel, I nevertheless found the appropriate conditions to continue developing my career. And I think that Israel developed an ecosystem where basically we learned from the American system how to absorb young people. The main question for a big university or for any university is how to bring young blood, young talented blood back in. I think we learned a lot from the American system, how we do it. We advertise positions, we collect many proposals, many applications, we shortlist them, we bring the shortlist back to the country, we listen to them, we interview them for several days, basically we grill them, and then we pick the one that we want to take as a young assistant professor to initiate his or her career. And I don't know about the system in Ecuador, but I think that, in my opinion, this is an excellent system because it's unbiased. You just pick up from the many applications you get. You will always find the most fitting, talented person to bring in. And I think that this is maybe one of the secrets of my country, of Israel, that it managed to really not build a big diaspora of Israeli benefiting the American economy, but bring them all back in order to benefit our own local economy.
Bueno, pues con esto damos por cerrado este coloquio, este conversatorio, y procedemos a devolverle la palabra a la moderadora de esta sesión.
Gracias también a nuestros distinguidos invitados nuevamente por participar en este enriquecedor conversatorio. Gracias, doctor Calvo, por su participación tan oportuna, precisa, interesante. Como hemos mencionado antes, desde el ESPOL nos complace poder recibirlos a todos y quisiéramos que se llevaran nuestros participantes un recuerdo de parte de esta comunidad politécnica. We also invite Dr. Yves-Marie Neher to give her a present from ESPOL. De la universidad, la doctora Cecilia Paredes, el doctor Paul Herrera, el doctor Carlos Monsalve y la doctora Paola Romero harán la entrega de estos obsequios a nuestros participantes. Gracias. Y para finalizar esta jornada pedimos a todos nuestros invitados, por favor nos ayuden con una fotografía de todo el auditorio. Deben, por favor, ponerse de pie quienes nos acompañan en sus respectivos asientos, esperar un instante para poder ubicarse y tomar la fotografía. Un aplauso, por favor. Y con esta última fotografía, que será un recuerdo de la magna visita, culminamos la jornada científica. Agradecemos a todos nuestros premios Nobel por compartir con nosotros sus experiencias y gracias a ustedes. Buen día.